Hi, Stat students. Let's get started on section 9.4, testing the difference between proportions. So far this chapter, we have tested the difference between means, both independent large samples and small samples, and then our paired samples or our dependent samples. So now we're going to proportions. So a researcher might ask if there's a difference between the proportion of customers who order salad or soup with their meals, or in the proportion of men who exercise regularly, is that less than the proportion of women who exercise regularly? So the questions, the statements, the claims all kind of come out the same. Our hypotheses are always going to be very similar to what we've done. So our null hypothesis is always population proportion 1 equals population proportion 2, because remember, we always assume that H sub O is true and they are equal, or there is no difference. So we can have, just like anything else, a two-tailed, so our proportions are not equal. We'd have to deal with alpha over 2 if that's the case. Left-tailed, our P1 is less than our P2, or our right tail, in which our population proportion 1 is greater than our population proportion 2. So all of those hypotheses look super similar. Now let's talk about what we need to do in order to get some, in order to calculate our test statistic. So the first thing we have is a new term, it's P-bar. P-bar is interesting because it is the weighted estimate. It's based on our hypothesis that they are equal, and sometimes this is called a pooled proportion. We're going to pool together all of our data. And when you see when I put up this formula, we're pooling together. So to calculate P-bar, we have to do X1 plus X2. So I'm going to go over here. X1 and X2 is our raw data from both of our samples. So that's the number of people from the men who exercise regularly and the actual number of people of women who exercise regularly over our two sample sizes. So we're taking that pooled percentage, we're putting those together. Our standard error of our difference, this is always our denominator. When we calculate our test statistic, we divide by our standard error. So our standard error, or our sigma, our population standard deviation of our p hat 1 and our p hat 2, that's a subscript down there, is equal to a giant radical of P bar, Q bar, times 1 over N1 plus 1 over N2. So P bar, we calculate our pooled proportion, and then we know that Q bar is going to be 1 minus P bar, right? So those two should add up to 1. When we multiply, they don't multiply to 1. So finally, our formula for finding our z-test value or test statistic is z equals a giant fraction of our p hat 1 minus our p hat 2 minus our population proportion 1 minus our population proportion 2. Remember, that will always go to 0 because we're assuming that they are equal. So if we subtract them, that would be a big old 0. And that's all over that standard error, so a giant square root of P bar Q bar times 1 over N1 plus 1 over N2. So similarities to our former formulas that we use. I'm going to zoom back up here so we can talk really quickly. So we know that X1 and X2 are raw data. Our P hat 1 is simply our sample 1 proportion. So the percentage of men who exercise regularly, going back to that first example. P hat 2 is our sample 2 proportion, so the percentage of women who exercise regularly. We all know what our N is, our sample size 1 and sample size 2. We need those in the standard error formula, and we need those to calculate our P bar. P1 and P2, we might not have actual numbers. In the previous chapter, we would say the number of people who have walked into someone while texting is this percentage. But we don't have actual data for our P1 and P2. We're going to make our assumption, remember, based on our null hypothesis that they're equal, and then we're going to have an inequality for our H sub 1, but no specific number. So obviously then to find Q1 and Q2, it's 1 minus our population proportion. And to calculate Q bar, this guy kind of got stuck at the middle, but, right, P bar is our x1 plus x2 over n1 plus n2, our Q bar is just 1 minus that. All right, so the other thing that I want to say when you are calculating these things is make sure that you go to, let's say, P bar, P hat, and then all the others, Q bar, Q hat, everything else. Please go to 3 decimal places. So those will all be calculations. Z, remember, we typically just go to 2 decimal places because then we go to the Z table. I should put that down as well. Since we are calculating our Z test statistic, we are going to use our Z table. But when you are putting numbers into your test statistic calculation, please go to 3 decimal places. It'll make life easier. And we're a little bit more precise. The more decimal places, the closer we are to the actual calculation. Otherwise, we're rounding early and we're using rounded numbers. So there are assumptions for the Z-test. We talk about these in every section. Typically, they're conditions that we have to check. I don't ask you to check them, but I want you to be aware of them. We do know that our samples must be random. We also know that our samples must be independent. And we've looked at this before. For both samples, our n times p has to be greater than equal to 5, and our n times q has to be greater than equal to 5. Technically, since we've got 2 proportions, we should, if we were checking this condition, check our n1 times our p1 and make sure that that is greater than or equal to 5. Our n2 p2 greater than or equal to 5. And then we would also need to check our n1 q1 and our n2 q2. So if we were checking conditions, we would have to check all 4 of these. And when we do our hypothesis test, we're using the same 5-step test, except please notice we have to do this side math. Just like we had to do side math for our dependent samples for means, we've got to do some calculations on the side. P hat and Q hat are easy. P bar, remember our pooled proportion, just a little bit of side stuff that we've got to do. So let's go through an example. Let's talk about seatbelt use. In a random sample of 200 men, 130 said that they used seatbelts. So that would be our information for sample 1. So we're going to say that in a sample of 200 men, 130 said they used seatbelts. So let's make this sample 1. So over here on the side, I'm going to jot down a couple things. So for sample 1, our N1 is 200 men. Our P hat 1 will be 130 out of that 200, which calculates to 0.65, I believe. No 3 decimal rounding there because that was nice and neat. In a random sample of 300 women, so our sample size 2 is going to be 300, 63 said that they used seatbelts. So our P hat 2 will be 63 out of 300. That's a really big difference. That's going to be something like a 0.21. And then don't forget, we also have to find our pooled proportion. So we're going to find our P bar. So P bar, we take our 2 x's. So our 130 plus our 63 over our 2 sample sizes. So 200 plus 300. When we calculate that out, that comes out to a 0.386. Again, 3 decimal places. So I can find Q bar then, right? That one's easy. I can find Q hat 1 and Q hat 2. Let's get over here and start with the test, and we can calculate as we go. So step one, my null hypothesis is always going to be that the proportion of men is equal to the proportion of women who use seatbelts. My H sub 1, it says test the claim that men are more likely to use a seatbelt. So that means this is a one-tailed, more specifically a right-tailed test, because we've got a more in there instead of a is there a difference. And this would be my claim. So step 2, we're going to go ahead and calculate our test statistic. So we've got a Z equals, I should have copied over that formula. We know we're going to do p hat 1 minus p hat 2. So a 0.65 minus a 0.21. Remember, it's minus 0. And then in my denominator, I've got my p bar 1, or my p bar, which was a 0.386, times my q bar, which would be 1 minus 0.386, which is going to be 0.614. And that's all over 1, or that's all times 1 over my sample size 1 plus my sample size 2 in the denominator. So again, it's a feat of magic to try to get your calculator to work for you. This one is actually a super ridiculous test statistic. I should have fixed my numbers a little bit, but I got a 9.90. It's okay. Huge difference, right? So that means for step 3, when I go to find my p-value, I'm going to go to my Z table with a 9.90. That falls off the table, so it tells me to use 0.9999. And it's a 1 minus because it's on the positive side. We always want that alpha to be little. So p equals 0.0001. So for step 4, I'm going to go ahead and I am going to compare my p-value, my 0.0001, to my alpha. No alpha over 2 in this case, remember, because 0.01. It's a one-tailed test, so my p-value is definitely incredibly less than my alpha, which means I am going to reject H sub O. Rejecting H sub O, remember, means that I do not think that they're equal. So I would say something like, there is enough evidence to support the claim that men are more likely to use a seatbelt. And we can write that all in there and go from there. I won't take your time to do that. Last but not least, let's go ahead and talk about the confidence interval. So confidence interval for the difference between two proportions looks like this. P hat 1 minus P hat 2, plus and minus my Z of alpha over 2, times, this one's where all this extra stuff comes in, so square root of P hat 1 times Q hat 1 over N1. We have not used Q hat 1 in this problem yet, so we have to go back to our side math and do our 1 minus 0.65. And then that's plus P hat 2, Q hat 2 all over N2. So we've got to go ahead to our P hat 1 or P hat 2 and do our subtraction there. And I believe that would be like a 0.79 or something like that for my Q hat 2. And in the middle of my test statistic, or in the middle of my confidence interval, I would have a P1 minus P2. So remember, if 0 is in the interval, it supports do not reject H sub O. Because we like that they are equal to each other. If 0 is not in the interval, that supports reject H sub O. I'm not going to do this hypothesis test because if I'm remembering right, it was that men are more likely, which means it's a one-tailed test. We only do confidence intervals for two-tailed tests, so we're just going to leave it here, and we'll practice this more. Have a great day. That is it for section 9.4.